Tonight, we're going to talk about the fact that most of the universe is already gone. Not gone in the sense of destroyed, gone in the sense of permanently out of reach. Not far away, not difficult, not a matter of building something better, unreachable by anything, ever, no matter how long anybody waits or how fast they learn to travel. The figure people who work on this arrive at is around 94%. 94% of the galaxies you can see in a long exposure of a dark patch of sky are already on the wrong side of a line, and nothing that leaves here tonight could catch them if it left at the speed of light and never stopped. And the number is still climbing. Roughly 160 billion stars cross that line every year. That is happening now. Some of them will cross it while this video is playing. So the universe is not sitting still and waiting to be explored. It is leaving. It has been leaving for about 5 billion years, and the overwhelming majority of it has already left. You are living on a world in the middle of an emptying room. I want to be careful with how that gets said, because it sounds like a metaphor, and it is not one. It is a description of what is measured to be happening, and the reason it happens is stranger than the fact itself. By the end, you'll know how much has gone, what took it, and why the strangest consequence is not about us at all. It is about whoever is here in 100 billion years, who will look up at a black and empty sky, work out what kind of universe they live in, and get the answer completely wrong. Tonight comes in pieces, and each one stands on its own. If you drift off partway through, nothing later depends on what you missed. Start with what is out there, because the scale is the part that has to land first. Point a large telescope at a patch of sky that looks completely empty. Not a famous patch, a boring one, the size of a grain of sand held at arm's length, chosen partly because there is nothing obvious in it. Leave the shutter open for days. What comes back is not empty, it is full of galaxies, thousands of them, in a patch that looked like nothing, each one containing 100 billion stars or more. The first time anybody did that, it was close to a career-ending decision. In 1995, the director of the institute running the Hubble telescope had a block of time he could use at his own discretion. Telescope time is fought over viciously. Proposals are reviewed, ranked, and mostly rejected, and getting 10 consecutive days on the best instrument in existence would normally require an extraordinary case. He decided to spend it staring at nothing. The plan was to pick a patch of sky with no known objects in it, nothing bright nearby, nothing anybody had any reason to look at, and leave the shutter open for 10 days. A number of colleagues told him it was a waste. The likely outcome, on the reasoning available at the time, was a black rectangle. 10 days of the most valuable equipment ever built, producing a photograph of nothing, with his name on the decision. He did it anyway. What came back had roughly 3,000 galaxies in it. One thing first, if you want more nights like this, subscribe. That's all I'll ask. Back to it. That single image changed what people understood about the scale of the universe more than almost anything else in that decade, and it was taken by pointing at the emptiest thing anybody could find. It has been repeated several times since, with longer exposures and better equipment, and it works every time, in every direction. There is no patch of sky that comes back empty. There has never been one. Counts of how many galaxies are out there have moved around a lot. A widely quoted figure from 2016 put it near 2 trillion, and that number has been argued down since as instruments got better at telling faint galaxies apart from noise. Whatever the true count, it is a number with at least 11 digits in it. Every one of those is a galaxy, not a star. A galaxy with its own hundreds of billions of stars, its own planets, and its own long history. It is worth saying that slowly, because the word galaxy gets read as a synonym for a lot of stars, and it is not. Every point of light you have ever seen in the night sky, with your own eyes, every single one, is a star inside this galaxy. All of them. The few thousand visible from a dark site are the nearest members of one system among that 11-digit total. You have never seen another galaxy with your unaided eyes except one faint smudge, and even that requires you to be somewhere genuinely dark and to know where to look. So the sky you know, the one you have looked at your whole life, is a local view of one galaxy, and it is already more than anybody can count. That is what is out there, not a sky with some things in it, A sky that is solid with galaxies in every direction, at every depth, as far as anything has ever been able to look. 94% of it is already unreachable. It is worth cashing out what a galaxy actually is before going further, because the word gets used so often that it stops meaning anything. Our own is a spiral roughly 100,000 light years across, containing somewhere between 100 and 400 billion stars. Light, which crosses from here to the moon in a second, takes 100,000 years to cross it. The sun is one star in it, sitting about 2/3 of the way out from the center, in an unremarkable position, going around once every 230 million years or so. The last time this solar system was where it is now in that orbit, the first dinosaurs were appearing. That is one galaxy. Now put a number with 11 digits next to that. There is no useful way to hold both of those at once, and I'm not going to soften it by offering a comparison that makes it feel manageable. It does not become manageable. The honest response to the number is that it does not fit in a human head, and that is fine, and the number is still correct. What matters for tonight is only this. Whatever that total is, 94% of it is on the far side of a line, and the line is not a distance anybody can travel. Now the part that trips people, because the obvious objection is a good one. The natural assumption is that unreachable means too far, that it is a matter of distance and speed, and that a sufficiently patient traveler with a sufficiently good ship would eventually get there. That is how distance normally works. Anywhere on this world can be reached given enough time. The moon can be reached, Mars can be reached, even the nearest star, at 70,000 years with current speeds, is a problem of patience rather than possibility. This is not that. Space itself is expanding, not the galaxies moving through space, the way a ship moves through water. The space between them is getting larger, everywhere, all the time, which means the distance to a far galaxy is growing without anybody moving, and the further away something is, the more space there is between here and there, and therefore the faster that gap grows. Past a certain distance, the gap between here and there grows faster than light can cross it. A beam of light leaving right now, aimed at one of those galaxies, would travel forever and never arrive. Not because it is slow, because the road ahead of it is being lengthened faster than it can cover ground. That is what unreachable means here, and it is why it is permanent. There is no ship that fixes it. Light is the fastest thing there is, and light does not make it either. Everything beyond that line is not far away, it is disconnected. There is a common misunderstanding worth clearing up, because it makes the whole thing sound like it breaks the rules. Nothing is moving through space faster than light. That rule holds and has never been violated. What is happening is that space between 2 points can grow at any rate at all, because that is not motion in the sense the rule was written about. Two galaxies can each be sitting still, doing nothing, and the distance between them can grow faster than light. Neither is moving. The gap is. That is a genuinely strange thing to accept, and it took physics a long time to accept it, and it is not a loophole or a technicality. It is how the universe is built. So the honest description is this: there is no barrier out there, nothing stops you. You could aim a ship at one of those galaxies and fire the engines and travel toward it forever, and the distance would grow the whole time, and you would never close it, and nothing would prevent you from trying. The most distant thing anybody can ever touch is not defined by how good the ship is. It is defined by geometry. Now the number that makes this feel like something rather than a fact. The light from those galaxies is still arriving. You can still see them. Every one of those thousands of smudges in that patch of empty sky is visible right now, tonight, and a good part of them are things nothing from here will ever reach. We can look at them. We cannot go to them. And the looking will not last forever either, because as the gap widens, their light gets stretched, and dimmer, and redder, until eventually it is stretched past anything anybody can pick up. They do not blink out, they fade, over an enormous stretch of time, and then they are simply not there anymore. So the sky you can see tonight is the fullest it will ever be. Every future night has fewer things in it than this one. Not noticeably, not in a human lifetime, or in a million of them. But the direction is fixed and it does not reverse, and there is a specific consequence of that which is the strangest idea in tonight's video. Somebody will be alive at the end of that process. and what they see will lie to them. In 2007, two physicists published a short paper working out what the sky will look like in the very far future, and what anybody alive then would conclude from it. Their names were Lawrence Krauss and Robert Scherer, and the answer they arrived at is the most unsettling thing in tonight's video, and it has nothing to do with anybody dying. Here is the situation they described. Run the clock forward 100 billion years. Everything not held to us by gravity has drifted past that line and faded out. What remains is our own galaxy and its neighbors, which are bound together tightly enough that the expansion cannot pull them apart, and which by then will have merged into a single enormous collection of stars, one galaxy, nothing else visible in any direction, at any distance, with any equipment. Now put somebody in that galaxy who is curious and intelligent and careful. Give them everything we have, better instruments than ours, better mathematics, unlimited patience, and no reason at all to be wrong. They look up, they see stars, all of which belong to the one galaxy they live in. Beyond that, blackness, not sparse, empty. They measure everything they can measure. They find no other galaxies, because there are none to find. They find no sign that anything is moving away, because everything they can see is bound to them and moving with them. And so, working carefully from the evidence in front of them, they conclude that the universe consists of a single island of stars sitting in an infinite void, and that it is not expanding, and that it has probably been that way forever. Every one of those conclusions is wrong, all of them, and there is no experiment available to them that would show it. That is the finding, and I think it is worth sitting with for a moment rather than moving straight on. They would not be careless. They would not be unscientific. They would do everything right and reach a false picture of reality, because the evidence that would correct them will have left. The three things that tell us what kind of universe we live in are all temporary. The first is that we can see other galaxies at all. That sounds too obvious to count as evidence, and it is worth remembering how recently it was in doubt. In April of 1920, two astronomers held a public debate in Washington about the size of the universe. One argued that the Milky Way was the entire universe, and that the faint spiral smudges in the sky were clouds of gas inside it. The other argued that those smudges were separate galaxies, enormously far away, each one comparable to our own. Nobody could settle it. Both positions had reasonable evidence, and the debate ended without a winner. 4 years later, a man named Edwin Hubble, working with what was then the largest telescope in the world, found a particular kind of variable star inside the Andromeda smudge. That kind of star has a useful property. How long it takes to brighten and dim tells you how bright it really is, so how dim it looks tells you how far away it is. The answer he got put, Andromeda far outside the Milky Way. It was not a cloud, it was another galaxy. He is said to have written the result on a photographic plate and sent it to the astronomer who had argued for the small universe, who reportedly said that the letter had destroyed his universe. That was 1924. Within one human lifetime, the universe went from being one galaxy to being billions. Everything anybody knows about cosmology rests on that discovery, and it was possible only because there was another galaxy close enough to resolve individual stars inside it. Take away the other galaxies, and there is no great debate to settle, because there is nothing to argue about. There is one galaxy, obviously, and no evidence to suggest otherwise, and nothing to suggest what the alternative would even be. The second is that their light is stretched by an amount that grows with distance. That is what showed the universe is expanding, and running it backwards is what gave us a beginning. The third is a faint glow that fills the whole sky, the leftover heat of that beginning, which arrives from every direction at once. It is the single strongest piece of evidence that there was a Big Bang. Every one of those three is on a timer. The galaxies leave, the stretched light leaves with them, and the leftover glow gets stretched too by the same process, until its wavelength is longer than anything that could be built to catch it, and then it is simply not detectable anymore. Krauss and Scherer worked out roughly when, within about 100 billion years, the other galaxies are gone from view. The leftover glow becomes undetectable on a comparable schedule. After that, the universe still had a beginning, it is still expanding, and there is no longer any way to find that out from inside it. The word they used was that cosmology becomes impossible. Not difficult, not expensive, impossible because the information is not in the universe anymore. It is worth spending a moment on that third piece of evidence, the leftover glow, because most people have heard of it, and very few have had it explained in a way that stays. For roughly its first 400,000 years, the universe was too hot and too dense for light to travel. Every photon was immediately absorbed and thrown back out again by the charged particles filling everything. It was opaque, in the way fog is opaque, everywhere, all at once. Then it cooled enough for the particles to combine into neutral atoms, and abruptly the fog cleared, and light could travel freely for the first time. That light is still traveling. It has never stopped. It has been crossing space ever since, and it is arriving here tonight from every direction at the same intensity. It is genuinely everywhere, including in the room you are in. If you are old enough to remember an analog television tuned between stations, the snow on the screen and the hiss from the speaker were mostly electrical noise from the set itself. But a small fraction of it, roughly 1 part in 100, was that glow arriving from the beginning of the universe and being picked up by the aerial. You were watching the oldest light in existence and finding it annoying. The two men who first identified it in 1964 thought it was a fault in their equipment. They spent months hunting for the source of a hiss they could not remove. They cleaned pigeon droppings out of the antenna, on the theory that the birds nesting in it were the problem. The hiss stayed. It came from every direction equally, which is not how faults behave. And eventually somebody pointed out that this was exactly what the leftover heat of the beginning would look like. They received the Nobel Prize for a noise they had been trying to get rid of. The pattern in it is extraordinarily detailed, and it is what almost everything we know about the early universe comes from. Its temperature varies by tiny amounts from place to place, and the pattern of those variations encodes the composition of the universe, its age, its geometry, and the seeds of every galaxy that later formed. It is the single most information-dense thing anybody has ever measured, and it is being stretched by exactly the same process as everything else. Every year it arrives a little longer in wavelength, and a little fainter, and at some point it stretches past anything that can be built to catch it, and then the most detailed record of the beginning is simply not available anymore. Not destroyed, just out of reach, in the same way the galaxies are. Now the part that turns this around and points it at us, which is why it belongs in the first half of tonight, rather than the last. If that is true of the future, the obvious question is whether it is already true of us. There is no rule that says the erasure started recently. There could easily be things that were knowable 100 billion years ago, and are not knowable now. Whole categories of evidence that expanded past the line before anybody was here to look. We have no way to check. That is the whole problem. Anything that has left is, by definition, not available to be examined. So the honest position is that we might already be in a version of the same situation, holding a picture of the universe that is correct as far as it goes, and missing pieces we have no way to know are missing. I want to flag clearly that this is speculation rather than a finding. Nobody has evidence that something has already been lost, precisely because that is the kind of thing you cannot have evidence for. It is worth saying out loud because it follows from the same argument, and it is worth labeling as speculation because it is not the same kind of claim as the rest. What is not speculation is our position in the timeline. The universe is about 13.8 billion years old. The other galaxies remain visible for something like 100 billion years. So the window in which the universe is readable from the inside is roughly the first 0.1% of the time anybody could be here to read it. We are inside that window, comfortably inside it, near the very beginning of it, not because anybody arranged it, because we happen to have turned up early on a world that formed early, around a star that formed early, which means the extraordinary thing about right now is not that we have telescopes, it is that there is still something to point them at. Every fact about the shape and history of the universe that anybody will ever know is being collected in a window that is closing, by a species that has been able to do it for about a century on a world with a fifth of its own habitable time remaining. That is not a warning about anything. Nobody can act on it. It is simply an unusual position to be in, and it is worth knowing that you are in it. There is one more turn in this, and it is smaller and sadder than the rest. The people in that far future galaxy would not know they were missing anything. That is the part that does not sit well. They would not feel the gap. Their picture would be complete and self-consistent, and every check they ran would agree with it, and they would have no reason to suspect that 100 billion years earlier the sky had been full of things. They would not be looking at an empty universe and wondering where everything went. They would be looking at what they thought was everything. And whether we are doing the same thing right now, at a smaller scale, is a question that cannot be answered from here. What can be answered is how much has already gone, and the light still arriving from it is the strangest evidence anybody has. There is a galaxy called GNZ11, and the light arriving from it left about 13.4 billion years ago, when the universe was around 400 million years old. You can see it, it has been photographed. It is one of the most distant things anybody has ever picked up, and it is roughly 32 billion light years away right now, which is more than twice the age of the universe expressed in light years, and nothing from here will ever get within reach of it. That combination is the strangest thing about the sky, and most people have never had it put to them plainly. The light left when the universe was very young. It has been traveling ever since. The whole time it was traveling, the space it was crossing was expanding, so the journey kept getting longer while the light was making it. It arrived anyway, eventually, because it set off early enough and the expansion was slower back then. Nothing leaving here tonight has that advantage. The expansion has sped up since. The road is being lengthened faster now than it was then. So the light got through and we cannot go back along the path it took. The route closed behind it. That is true of an enormous fraction of what you can see. The sky is full of things whose light made the trip during a window when the trip was still possible, and which are now on the far side of a line nothing can cross. I find that the single most affecting fact in this whole subject, and it takes a moment to settle, you are looking at things that are permanently unreachable, and the only reason you can see them at all is that their light left before the door shut. It is worth putting a shape on how far away that actually is, because 32 billion light years is a number that slides straight off. Light crosses the distance from here to the moon in a little over a second. It crosses from the sun to here in about 8 minutes. It takes about 4 hours to reach Neptune. Those are the distances inside this solar system, which took a spacecraft launched in 1977 nearly half a century to cross. The nearest star is 4 years of light travel. The center of our own galaxy is about 26,000 years. Andromeda is 2.5 million. GNZ11 is 32 billion. That is more than 12,000 times further than Andromeda, which is itself the most distant thing most people can see with their eyes. And Andromeda is a neighbor. It is close enough that gravity holds us together. There is a further oddity in this that catches people out. The galaxy that sent that light does not look like that anymore. What you see is a young galaxy, 400 million years after the beginning, small and irregular and furiously forming stars. Whatever it is now, 13.4 billion years later, is something else entirely, probably much larger, probably having merged with other galaxies several times over, probably quiet. We will never see that version. The light showing its current state will never arrive. What we have is a photograph taken 13.4 billion years ago of something that no longer exists in that form, of a place nothing from here can ever go. Now what happens to that light? Because it does not stay the way it started. While light is crossing expanding space, the space it is inside of stretches, and the light stretches with it. A wave that set off short arrives long. For visible light, longer means redder, so light that left a young galaxy as brilliant blue and white arrives here, shifted toward the red end, and if it has been traveling long enough, it arrives past red entirely, in the infrared, invisible to any eye. That is why the most distant galaxies are found with instruments built to see heat rather than light. The James Webb Telescope exists in the form it does largely for that reason. The oldest things in the sky are not faint blue smudges. They are infrared because the universe stretched them out of the visible range on the way here. And the stretching does not stop. It continues for as long as the light is in flight, and it continues for every galaxy still sending light our way, which sets up what actually happens to the 94%, because it is not what people expect. They do not disappear. There is no moment where a galaxy blinks out and the sky has one fewer thing in it. What happens is slower and stranger. As a galaxy is carried further away, its light arrives more stretched, and the stretching also means it arrives less often, because the waves are spaced further apart in time as well as in distance. So the galaxy dims, and reddens, and dims further. From our side it fades toward a limit, taking an enormous stretch of time to do it, never quite blinking out but becoming steadily fainter and steadily redder until whatever is left is beyond anything that could pick it up. A galaxy crossing that line is not a sudden event, it is a very long fade, and the crossing itself has already happened by the time anybody could notice. The ones that have crossed already are still visible tonight. That is worth being clear about, because it sounds like a contradiction and it is not. 94% of them are unreachable, and almost all of them are still perfectly visible. Unreachable and invisible are different lines, and the reachable line closed a long time ago while the visible line is still a long way out. So the sky is showing you an enormous number of things you cannot get to, and it will keep showing you a lot of them for billions of years, and the number shown is going down the whole time. There is one more thing about the light worth knowing, and it is the reason the newest telescopes look the way they do. An instrument built to catch heat cannot be warm itself, because its own warmth drowns out what it is trying to see. So the James Webb Telescope has to be kept at around -370 degrees Fahrenheit, which is a few degrees above the lowest temperature that exists. Getting it that cold is why it has a sunshield the size of a tennis court, made of 5 separate layers, each thinner than a human hair. The layers block the sun, and the gaps between them let the heat that does get through radiate sideways into space, instead of continuing inward. It works. The far side of that shield sits at roughly the temperature of deep space, and the telescope behind it can pick up warmth from galaxies whose light left when the universe was a few 100 million years old. It also means the instrument cannot be repaired. It sits about 1 million miles from here, in a position where the sunshield can stay pointed correctly, which is 4 times further away than the moon, and far beyond anywhere anybody could reach. The Hubble telescope was serviced 5 times by people in spacesuits. This one gets no visits. Everything about it had to work correctly the first time, including a deployment sequence with 344 separate steps, any one of which could have ended the mission. All of that engineering exists because the universe stretches light on its way here, and the oldest light has been stretched out of the visible range entirely. The most complicated object ever launched exists to see things that are red because they are leaving, and that is worth holding on to, because it says something about where we are rather than about the engineering. We built the hardest thing anybody has ever built, put it 1 million miles away where nobody can ever fix it, and cooled it to within a few degrees of the coldest temperature that exists, so that it could catch the light of worlds we will never reach, sent by galaxies that have already been carried out of range. Nothing comes of it. There is no destination, no arrival, nothing anybody gets to do with what it finds except know it. That is the whole return on the investment. Knowing. Looking at something you have no possible relationship with, working out what it is, and then dying, and passing the answer to whoever comes next. You could call that pointless, and it would be difficult to argue against on strictly practical grounds. I think it is the least pointless thing this species has ever done, and I am aware that is a preference rather than an argument. There is a way to put a shape on the loss, and it is unpleasant. Roughly 160 billion stars cross out of reach every year. That is not stars dying. Those stars are fine. They will go on shining for billions of years, and there may be worlds around them with things living on them, and every one of those is now permanently disconnected from everything here. 160 billion a year is around 5,000 a second. While you have been listening to this, the number of stars anything from here could ever reach has fallen by more than 1 million. That figure keeps running whether or not anybody is paying attention to it. It ran through every war and every empire, and every quiet afternoon in history. It has been running at roughly that rate for about 5 billion years. which is longer than this world has existed in its current form. Nothing about it is dramatic from the inside. There is no sound, no visible change, nothing anybody could have noticed at any point. The sky tonight looks exactly like the sky 1,000 years ago. And the total amount of universe available to anything that starts here has been falling the entire time. Which raises the obvious question, and it is the one people ask as soon as they follow this far. Was there ever a moment when more of it was reachable, and did we miss it? The answer is yes, and the amount we missed is not small. Andromeda is coming toward us at about 250,000 miles per hour, and last year the certainty that it will hit us collapsed. That is worth taking slowly, because for most of the last 2 decades, this has been presented as settled fact, and it was in a great many books and videos, including some I would have made myself. Start with what Andromeda is. It is a spiral galaxy about 2.5 million light-years away, and it is the most distant thing most people can see without help. On a genuinely dark night, away from towns, it is a faint smudge about the width of your little fingernail, held at arm's length. It looks like a small grey cloud that will not come into focus. That smudge is 1 trillion stars. The light reaching your eye from it left 2.5 million years ago, before anything recognizably human existed on this world. It has been crossing empty space the entire time our whole species has come into being, and it is one of the very few large things in the sky that is getting closer rather than further away. That is a clue that something different is going on with it. Almost everything else out there is receding. Andromeda is approaching at around 110 kilometers a second, which is roughly 250,000 miles per hour. The reason is simple. It is close enough that gravity between it and us is stronger than the expansion trying to separate us. Inside a certain radius, expansion loses. We and Andromeda are inside each other's radius, and so we are falling toward each other rather than drifting apart. The story built on that has been in circulation since about 2012. Andromeda and the Milky Way collide in roughly 4.5 billion years, tear each other apart, and settle over another few billion years into one enormous ball of stars, which somebody nicknamed Milkomeda. It was a good story and it was well supported, and it is now in serious doubt. In 2025, a team led by a researcher named Til Sawala published work that redid the calculation with more care about what is uncertain in it, and the result was that the chance of a merger in the next 10 billion years is close to 50%. One of the researchers described it as going from near certainty to a coin flip. The reason is not that anybody made a mistake, it is that the question turns on quantities nobody knows precisely. The mass of our own galaxy is known to roughly 20%. That sounds accurate, and for this purpose it is not, because the whole outcome depends on how hard the two are pulling on each other, and there is a sideways problem that had been underweighted. There is a smaller galaxy near us called the Large Magellanic Cloud, visible from the southern hemisphere as a detached patch of the Milky Way. It is heavier than people used to think, and it is pulling our galaxy off to one side, out of the plane the 2 large galaxies would otherwise be moving in. A small nudge now becomes an enormous difference over billions of years. Pulled slightly off course, the 2 galaxies swing past each other instead of into each other, and the merger does not happen, or does not happen for a very long time. Meanwhile, a galaxy on Andromeda's side pulls the other way, so the answer depends on the mass of things nobody has weighed accurately, and the honest current position is that nobody knows. There is a date attached to when that improves, and it is soon. More precise measurements of how Andromeda is moving sideways across the sky are expected this summer, which should narrow the range considerably. That is a genuinely open question, with a resolution arriving within months, which is not something you can say about much in this subject. There is something worth saying about how this kind of correction happens, because it is the second time tonight a confident story has softened, and it will not be the last. Nothing went wrong. The 2012 result was careful work using the best information available. What changed is that better information arrived, particularly about the mass of a nearby galaxy that had been treated as a minor detail. The response was not to defend the earlier answer, it was to redo the calculation properly, including the uncertainties that had been glossed over, and publish a result that says the honest thing, which is that nobody knows. That is unglamorous, and it is the whole reason any of this can be trusted. It is also worth noticing what it does to everything you have ever been told about this subject. There are documentaries, articles, and videos in circulation right now, stating the collision as settled fact, made before last year, all of them perfectly reasonable when they were made, and all of them now out of date. Some of what I am telling you tonight will go the same way. I do not know which parts. That is not false modesty. It is just what happens in a field where the information keeps improving. The parts most likely to move are the ones with precise numbers attached to distant futures. The parts least likely to move are the ones already measured, like the 94%, which is arithmetic from things that have already been observed rather than a projection. Now, what a collision between galaxies actually is, because it is not what the word suggests. Stars almost never hit each other. Galaxies are overwhelmingly empty. The distance between stars, compared to the size of stars, is so large that two galaxies can pass completely through one another, and the chance of any two stars striking is close to zero. What happens instead is gravitational. Orbits get disrupted. Stars get flung into long streams. Clouds of gas, which are enormous and diffuse, do slam into each other, and that compression triggers an intense burst of new star formation. The whole process takes hundreds of millions of years. There is no moment of impact. Anybody watching would see the sky change over timescales far longer than any civilization has ever lasted. What it would look like from here, if there were anybody here, is worth describing, because it is the one thing about this that is genuinely spectacular. Andromeda tonight is a faint smudge you need a dark sky to notice. As it approaches, it gets larger. Not quickly. Over hundreds of millions of years, it grows from a fingernail to a hand to something spanning a large part of the sky. Long before any collision, it would be the dominant object at night. A second galaxy, seen face-on, filling a substantial fraction of what you can see, with its spiral arms visible to the naked eye. Then the two would begin to distort each other, long streams of stars pulled out of both, arcing across the sky. The gas clouds colliding and igniting into intense bursts of new star formation, which would make parts of the sky considerably brighter than anything visible now, and all of it unfolding so slowly that any single generation would see a sky that looked completely static. If it happens, the sun is not destroyed. It is most likely thrown into a different orbit, possibly much further out, possibly on a path that takes it well away from where it sits now. Except that by then the sun will not be the sun anymore, which is the part that puts the whole question in perspective. In 4.5 billion years, the sun is at or past the end of its ordinary life. This world's oceans will have been gone for billions of years. Whatever is here to see a galaxy merger, if there is anything, will not be anything that started here in a form we would recognize. So the collision is a real question, and it is not a question about us. And here is why it belongs in tonight, rather than in a different video. It does not matter, for the thing this video is about, whether they merge or not, Andromeda and the Milky Way are bound to each other by gravity. That is settled, and it is not what the coin flip is about. The coin flip is about whether they merge soon, or swing past each other and merge much later, or orbit for an extremely long time first. Either way, they stay together. Neither of them is going anywhere. They are inside the radius where gravity beats expansion, and they will still be inside it in 100 billion years. Everything outside that radius leaves regardless, so the merger is a question about the furniture in the room. It has no effect on the fact that the room is emptying. Whether the sky in 5 billion years shows one galaxy or two, it will show fewer distant ones than tonight, and it will keep showing fewer, and the reason has nothing to do with Andromeda. That is a slightly deflating way to treat what was, for a while, the most famous event in the future of this galaxy. But it is the honest waiting. What actually matters for the long run is not the collision. It is the list of things that stay, which turns out to be short and specific and worth knowing by name. Anything from here will ever be able to touch fits inside a region about 10 million light years across, and there are roughly 80 things in it. That region has a name, It is called the local group, which is an unglamorous name for the entirety of what this corner of the universe gets to keep. It is worth going through what is actually in it, because the list is shorter than most people expect, and it is the permanent inventory. There are two large galaxies, ours and Andromeda. Between them they hold the overwhelming majority of everything in the group. There is one medium one, called Triangulum, about half the width of ours, and considerably lighter, sitting near Andromeda and probably orbiting it. And then there are dwarfs, somewhere between 50 and 80 of them, depending on how you count and how many faint ones have been found this year, because new ones keep turning up. Most are small enough that they would be unremarkable if they were not the only other things in the neighborhood. The two best known are visible from the southern hemisphere as detached smudges of the Milky Way, and both of them are in the process of being torn apart by our galaxy's gravity and absorbed. That process is worth a moment, because it is happening now, rather than in some distant future. Our galaxy eats its neighbors, not occasionally, continuously. When a small galaxy passes close enough, the pull on its near side is stronger than the pull on its far side, and that difference stretches it. Over hundreds of millions of years it is drawn out into a long ribbon of stars, which winds around the larger galaxy several times and eventually blends into it. There is a dwarf galaxy on the far side of the Milky Way center from us that is midway through exactly that. It was only found in 1994 because it sits behind the crowded core and was hidden in the glare. It has already been pulled into long streams. It has passed through our galaxy's disk more than once, and it is not going to survive as a separate object. There are other streams too, arcs of stars looping through the halo around us, each one the smeared remains of something that used to be its own galaxy. So the sky over this world contains the wreckage of at least a dozen absorbed neighbors, spread out so thinly that you would never notice, and identifiable only because the stars in each stream are all moving the same way. The local group is not a stable arrangement of 80 separate things. It is a collection in the process of becoming one thing, and it has been doing that since it formed. That is the whole estate. Now the reason it is permanent, which is the only genuinely good news in tonight's video. Gravity holds this group together, and expansion cannot pull it apart. That is not a hopeful reading. It is a straightforward consequence of the numbers. Inside a bound group, the gravitational pull between members exceeds the stretching, and the stretching simply loses. So while everything outside drifts off, the local group stays. Its members orbit each other, fall into each other, merge over billions of years, and eventually settle into one very large elliptical galaxy with no spiral arms and no new star formation worth mentioning. That object will still be there in 100 billion years. It will still be there in 1 trillion. It is the last structure in this part of the universe, and nothing will take it away. Which sounds like a reprieve until you put the numbers next to each other. The local group contains something in the region of a couple of trillion stars once you count both large galaxies and everything else. The part of the universe we can currently see contains something on the order of 1 billion trillion stars. So the permanent inheritance, the part that stays no matter what, is roughly 1 part in 500 million of what is currently visible. Everything else in that long exposure of an empty patch of sky is on loan, and it is being called in. I want to be honest, that a couple of trillion stars is not a small thing by any standard a person can hold. If you started visiting them at 1 per second, you would not finish in 100,000 years, and there are enough worlds in that group to occupy anything for as long as it could conceivably survive. The word poor is not the right one. The right word is closed. Whatever happens from here on, it happens inside a boundary that is already drawn, and nothing that starts inside it ever comes in. There is a version of that which is genuinely worth thinking about, and it concerns anybody else. Every argument about whether we are alone gets made about the galaxy, or occasionally about the local group, and there is a reason for that beyond convenience. It is that nothing outside the local group could ever reach us or be reached, no matter who is out there, or how long they last, or what they build. If a civilization exists tonight in a galaxy, 100 million light years away, and it is old and enormous and capable of anything, it does not matter. There is no contact available. The gap between us grows faster than anything can cross it. They are not distant neighbors. They are in a separate universe as far as any interaction is concerned. So the question of whether anybody else exists is a question with two completely different answers depending on what you mean. Somewhere out there, across those trillions of galaxies, the odds of somebody are difficult to argue with. Within the region that could ever matter to anything here, the sample size collapses to about 80 galaxies, most of them dwarfs, and the odds get much worse. That is a real narrowing, and it is not usually spelled out. There is something about the merged object that is worth describing, because it will be the permanent form of everything around here, and it is not much like what we have now. Spiral galaxies are spirals because they are rotating disks. All the material orbits in roughly the same plane, in roughly the same direction, which is why our own galaxy appears as a band across the sky rather than being spread evenly around us. Mergers destroy that. When two large galaxies combine, the orderly rotation is scrambled. Stars end up on orbits tilted every which way, and what results is not a disk at all. It is a rounded swarm, called an elliptical galaxy, with no arms, no obvious plane, and no structure beyond a general concentration toward the middle. The other thing mergers do is use up the gas. The collision compresses it, which triggers an enormous burst of star formation, which consumes it. Ellipticals are typically red and quiet, because their star-making material was spent long ago, and what remains are the long-lived stars that outlasted everything brighter. So the permanent version of this neighborhood is a large red swarm of old stars, no spiral arms, very little new star formation, sitting alone. The sky from inside it would look completely different. No band of light across the middle of the night, because there would be no disk to look along. Stars scattered in every direction instead, more or less evenly, thinning out toward the edges. Nobody would look up and see a galaxy. They would just see stars, in all directions, and nothing beyond them. There is one more consequence, and it is the strangest of the set. The local group is not just what we keep. It is also, eventually, all there is to look at. Once the last outside galaxy fades, the sky over that merged elliptical is the merged elliptical, and nothing else. Its own stars, its own dust lanes, and past them a blackness that never resolves into anything, no matter how long anybody looks or what they build to look with. Not a sparse sky, not a dim one, empty. And that emptiness is what will teach the wrong lesson, because a universe that looks like a single island of stars in an infinite void is exactly what a universe would look like if it had always been a single island of stars in an infinite void. There would be nothing to distinguish the two. Which brings up the obvious question: if this is what is happening, and if it can be worked out from here, then something must be pushing everything apart, and somebody must have found it. Somebody did, in 1998, and they were not looking for it, and they spent months assuming they had made a mistake. In 1998, two rival teams of astronomers, who had spent years trying to beat each other to the same result, both found the same thing, and both of them assumed they had made a mistake. They were not looking for what they found, they were looking for the opposite, and the fact that they were competing turned out to matter enormously, because when two groups who want different outcomes get the same answer, the answer is usually real. Here is what they were doing. Everybody knew the universe was expanding. That had been established in the 1920s. The obvious next question was how fast it was slowing down. Slowing down was the assumption, and it was a reasonable one. Everything in the universe pulls on everything else through gravity. An expansion made of things that attract each other should be losing speed, the way a ball thrown upward loses speed. The only real question was whether it was losing enough speed to eventually stop and fall back, or whether it would coast outward forever, getting slower and slower. That was the whole debate. Both possibilities were on the table, and either would have been a respectable answer. To settle it, you need to compare how fast things were moving apart long ago with how fast they are moving apart now, which means you need to see very distant things, because distant means long ago, and you need to know how far away they actually are. Knowing how far away something is turns out to be the hardest problem in this entire field. Brightness alone tells you nothing. A dim thing might be faint and close, or brilliant and far. To get a distance, you need something whose real brightness you already know, so that how dim it looks tells you how far off it is. The solution both teams used is a particular kind of exploding star, and understanding what it is makes the whole thing click. Some stars end their lives as white dwarfs, which are the collapsed remnant cores of stars like the Sun. A white dwarf is roughly the mass of a star packed into something the size of a world. It is not doing anything anymore. It is a cinder, cooling very slowly, and left alone it would sit there essentially forever. But if a white dwarf has a companion star nearby, it can pull material off it. Slowly, over a long time, it gains mass, and there is a hard limit on how much mass a white dwarf can hold. Past that limit, the object cannot support itself, and it detonates. The limit is the key to everything, because it is the same limit for every white dwarf anywhere. It is set by physics, not by circumstance. Which means every one of these explosions goes off at very nearly the same mass, and therefore releases very nearly the same amount of energy, and therefore has very nearly the same true brightness. They are, near enough, identical bulbs scattered across the universe. Find one in a distant galaxy, measure how faint it looks, and you have a distance. That is the tool. It is not perfect, and a great deal of careful work goes into the corrections, but it works. The limit itself has a story attached that is worth telling, because it shows how these things actually go. It was worked out in 1930 by a 19-year-old named Subramanian Chandrasekhar on a ship during a long voyage from India to England to begin his studies. He did the calculation to pass the time. When he presented it in London a few years later, the most eminent astrophysicist in Britain stood up after his talk and dismissed it publicly, and the ridicule stuck for years. Chandrasekhar eventually left the field of stellar structure entirely and worked on other things. He received the Nobel Prize for it in 1983, 53 years after doing the work on the boat. So the tool both teams used to find the expansion accelerating was built on a calculation that a teenager did out of boredom and that his field rejected for a decade. Now the result. Both teams found their distant exploding stars were fainter than they should have been. Fainter means further away than expected. Further away than expected means the universe had expanded more than expected in the time since that light left, which means it had not been slowing down at all. It had been speeding up. That was not on the list of possible answers. Nobody had a mechanism for it. An expansion made entirely of things that attract each other cannot accelerate, so either the observations were wrong or there was something in the universe nobody knew about. Both teams went hunting for the error. Dust between here and there could dim a distant star, so they checked for dust. Exploding stars long ago might be intrinsically different from ones nearby, so they checked that. Every check came back and the results stayed. One of the researchers, Adam Rees, has described going through the process of trying to make his own answer go away and failing, and eventually having to accept that the thing he was arguing against was what the sky was actually showing him. Both teams published in 1998, within a few weeks of each other, saying the same thing. The Nobel Prize came in 2011. Now the honest part, which is what all of this actually established and what it did not. It established that the expansion is accelerating. That is measured, and it has been confirmed many times over by completely independent approaches since. It did not establish what is doing it. The name for the cause is dark energy, and the name is a placeholder. It means the thing that is causing this, whatever it is not a theory, and it is not an explanation. It is a label on a box nobody has opened. That is worth being blunt about, because the phrase gets used constantly in a way that implies more than it should. When you hear that dark energy is pushing the universe apart, the honest translation is that something is pushing the universe apart, and we have agreed on what to call it. Nobody has detected it directly. Nobody has produced any of it. Nobody can tell you what it is made of, whether it is a substance at all, or whether the word energy is even appropriate. It is named after the two things known about it. It is dark, meaning it does not interact with light in any way anybody can find, and it appears to carry energy, because something is doing work. That is the entire content of the name. You are entitled to find that unsatisfying. Physicists find it unsatisfying. It has been the largest open problem in the field for a quarter of a century, and there is no consensus candidate. Estimates put it at roughly 68% of everything in the universe, ordinary matter, meaning everything you have ever seen or touched. Every star and world and person comes to about 5%. So the substance that is taking the universe away from us makes up 2/3 of it, and nobody knows what it is. The remaining 27% is a second thing nobody can identify, and it was found decades earlier by somebody who spent most of her career being ignored. In the 1970s, an astronomer named Vera Rubin was measuring how fast stars orbit inside galaxies. The expectation was straightforward. Most of a galaxy's mass sits near its center, so stars further out should orbit more slowly, the way the outer planets orbit the Sun more slowly than the inner ones. She found that they do not. Stars near the edge of a galaxy move about as fast as stars near the middle. That should not be possible. At those speeds, the outer stars should have been flung away long ago, and the galaxy should have come apart. The only way it holds together is if there is far more mass present than the visible stars account for, spread out through and around the galaxy, exerting gravity and emitting no light at all. She found the same result in galaxy after galaxy. It was consistent, it was unambiguous, and the field took a long time to accept it. She never received a Nobel Prize, and she died in 2016. The disagreement about whether that was an oversight is not really a disagreement. That unidentified mass is called dark matter, and it is a completely separate mystery from dark energy, despite the similar name. One holds galaxies together, the other pushes the universe apart. Nobody knows what either of them is. Put the numbers together, and the picture is genuinely absurd. About 5% of the universe is the kind of matter that everything you have ever encountered is made of. 95% is two things that have names and no explanations. Everything in tonight's video, every galaxy and star and world, is happening inside the 5%. The best current description is unsatisfying, and it is worth stating exactly. It behaves like a property of empty space itself. Every cubic inch of vacuum appears to carry a small amount of energy that pushes outward. And because empty space is created as the universe expands, there is more of it as time goes on, and so the push grows. That is why the acceleration got stronger. Early on, there was less space and more matter packed closer, and gravity was winning. Around 5 billion years ago, the balance tipped, and it has been going the other way since. There is an attempt at explaining it that produced what is generally called the worst prediction in the history of physics, and it is worth telling because of how badly it failed. Empty space is not actually empty according to quantum theory. At very small scales, it is full of activity, pairs of particles appearing and annihilating constantly, which is not speculation, and which has been confirmed in laboratories in several ways. That activity carries energy. So there is a natural candidate sitting right there. The energy of the vacuum itself might be the thing pushing space apart. The obvious move is to calculate how much energy that should be and compare it with how much is needed. The calculation has been done. The answer is too large by a factor with about 120 zeros after it. Not too large by a factor of 10, or 1,000, or 1,000,000. 120 orders of magnitude, which is the worst disagreement between a prediction and a measurement that anybody has ever produced in any field. If the vacuum energy were anywhere near what the calculation says, the universe would have been torn apart before a single atom formed. No stars, no worlds, nothing alive anywhere, ever. The fact that you exist is itself evidence that the calculation is wrong, which is an unusual position for physics to be in. Something is cancelling it out, almost perfectly but not quite. The amount left over, the amount actually pushing the universe apart, is what remains after a cancellation accurate to more than 100 decimal places. Nobody knows what is doing the cancelling, or why it stops just short of complete. So the most natural explanation for dark energy fails by the largest margin in the history of science, and nobody has a replacement that works. That gap has been sitting there for decades, and it is one of the most serious unsolved problems in physics. Einstein wrote something very like this into his equations in 1917. for entirely different reasons, and then removed it when the expansion was discovered and reportedly called it a blunder. It came back 80 years later as the dominant component of the universe. That is the state of it. A number 2/3 of everything, described by a term somebody added and withdrew a century ago, doing something nobody predicted for reasons nobody can explain. And the effect of it is the thing this whole video is about. It is what draws the line, and the line is closer than most people assume. The universe is 13.8 billion years old, and the furthest thing we can see is about 46 billion light years away. And those two numbers together confuse almost everybody who meets them. If nothing travels faster than light, and light has only had 13.8 billion years to travel, then nothing should be more than 13.8 billion light years off. That is the obvious arithmetic, and it is wrong, and the reason it is wrong is the same reason everything else tonight happens. While the light was traveling, the space it had already crossed kept expanding behind it. A galaxy sends light toward us when the gap is small. The light crosses that gap, but during the crossing, the ground it has already covered stretches out, and the galaxy itself is carried further away. By the time the light arrives, the thing that sent it is much further off than it was when it sent it. So the light took 13.4 billion years to get here, and the object that emitted it is now roughly 32 billion light years away. And both statements are true, and there is no contradiction between them. There is a smaller version of that happening to you constantly, and it is worth noticing. Every time you look at anything, you are looking at the past. The face of somebody across a room reaches you a few billionths of a second late. The moon is a second and a bit behind. The sun you would see if you looked up is 8 minutes old, and if it went out you would carry on in full daylight for those 8 minutes with no way to know. That is not a curiosity. It is the only way anybody has ever seen anything. There is no version of looking that shows you the present. What is different about the distant galaxies is only the scale. The delay is measured in billions of years instead of billionths of a second, and during a delay that long, the thing you are looking at has time to move somewhere you can never follow. The furthest edge of what we can see sits at about 46 billion light years in every direction. That is not the edge of the universe. It is the edge of the part we have had time to receive anything from. Now the second line, which is the one that matters for tonight, and which is much closer in. There is a distance beyond which anything we send can never arrive. Not light, not a ship, not a signal, nothing. Past that point, the gap grows faster than the fastest possible thing can close it, and it keeps growing, so the deficit only widens. That line sits at roughly 16 to 17 billion light years. Hold those two numbers next to each other, because the gap between them is the whole subject. We can see out to about 46 billion light years. We can reach out to about 16. Everything in between, which is the overwhelming majority of the volume, is visible and permanently untouchable. It is on the screen and not in the world, and because volume grows with the cube of the radius, the difference between 16 and 46 is far larger than it sounds. That ratio is where the 94% comes from. There is a detail here worth getting right, because it is the single most misunderstood thing in this area. Galaxies past a certain distance are receding faster than light. That is true, and it is not a violation of anything. The rule that nothing exceeds light speed is a rule about motion through space. It says that if you and I are standing in the same region, neither of us can move past the other faster than light. That rule has never been broken and is not being broken here. What is happening instead is that the space between two distant points is growing. Neither point is moving. Both are sitting still relative to their own surroundings. The distance between them is increasing because there is more space in between than there used to be. There is no speed limit on that, because it is not a speed in the sense the limit was written for. So a galaxy can be stationary, doing nothing, and be receding from us faster than light, and be perfectly obedient to physics the entire time. The consequence is that we can still see some galaxies that are already receding faster than light, because their light left long ago when the gap was smaller and the expansion was slower. It has been fighting upstream ever since, and it is still arriving. That will not last. There is a point at which the upstream fight becomes unwinnable, and after that no new light from that galaxy ever reaches us again. Everything we see of it from then on is older light still in transit, arriving more and more stretched, until that runs out too. Now the part that gives the whole thing its urgency, which is that the reachable line is closing. In a universe that was slowing down, the reachable region would be growing. More and more would come into range as time passed, because the expansion would be losing strength, and light would be gaining ground. That is the universe everybody assumed we lived in until 1998. In an accelerating universe, it runs the other way. The stretching gets stronger, and things that were reachable stop being reachable, one after another, permanently. The line does not move outward, it moves in. That is what the 160 billion stars a year figure is describing. It is the rate at which things cross from the reachable side to the unreachable side, and it is not a one-time event that happened in the past. It is a process that is running tonight. There is a complication in all of this that has been getting worse rather than better, and it is worth knowing because it affects every number in tonight's video. Nobody can agree on how fast the universe is expanding. There are two well-established ways to work it out, and they give different answers. The first works outward from nearby. You find objects whose real brightness you know, work out their distances, see how fast they are receding, and build a ladder from things you can measure directly out to things you cannot. That approach gives a figure around 73. The second works forward from the beginning. You take the leftover glow from the early universe, which carries a detailed pattern in it, and use what physics says should have happened since, to calculate what the expansion rate ought to be now. That approach gives a figure around 67. Those are not close, and the uncertainty on each has been shrinking for 20 years, which means the disagreement has been getting sharper rather than softer. Both methods have been checked repeatedly by different groups using different equipment. Nobody has found the error. It is entirely possible there is no error, and that something in the standard picture of the universe between the beginning and now is missing. That is not a small caveat. It means the number describing how fast everything is moving apart, which sets where the line falls and how fast it closes, is not settled to better than about 10%. The 94% figure survives that comfortably. The precise timings do not, and anywhere tonight where I have given a number of years, it is worth mentally attaching a wide margin to it. There is a way to make the closing line concrete that I find clarifying. Every galaxy currently sitting just inside the line has a deadline. Not a deadline for us to arrive, a deadline for anything to depart. If nothing sets out before that galaxy crosses, it can never be reached by anything from here, forever, under any circumstances. Most of those deadlines have already passed. That is what 94% means. It is worth being precise about when they passed, because the timing is not what people assume. For most of the history of the universe, the expansion was slowing, gravity was winning, because everything was closer together and pulling harder. During that entire stretch, the reachable region was growing. More came into range as time went on. That lasted for roughly the first 9 billion years. Then the balance tipped. Space had stretched enough that matter was thinly spread and gravity had weakened, while the push from dark energy, being a property of space itself, had not weakened at all. Around 5 billion years ago it took over, the expansion started speeding up, and the reachable region stopped growing and began shrinking. 5 billion years ago is roughly when this solar system formed. So this world came into existence almost exactly at the turning point. Everything that has happened here, the whole history of this planet from molten rock to whatever you would call the present, has taken place during the contraction of what is reachable. That is a coincidence, with no meaning attached to it. There is no reason for the two to line up, and nobody claims there is one. But it does mean that this world has never existed in the universe where things were getting closer. Not for a single day of its history. For the remaining 6%, the deadlines are stacked up across the coming billions of years, and each one that passes removes a target from the list permanently. Nobody is going to meet any of them. That should be said plainly rather than left implied. Nothing built here has left this solar system in any serious sense, and the fastest object we have ever launched would take 70,000 years to reach the nearest star, which is inside our own galaxy and roughly 4 light-years away. The deadlines are for journeys of millions and billions of light-years. So the 6% is not an opportunity anybody is losing. It is a bookkeeping exercise about a set of places nothing from here was ever going to visit, which raises a reasonable objection, and it is the right one to raise. If none of it was ever reachable in practice, does it matter that it is becoming unreachable in principle? I think it does, and the reason is not practical. It matters because it changes what kind of universe this is. A universe where everything is in principle connected, where any 2 points could eventually communicate given enough patience, is a different object from one that is fragmenting into permanently separated islands. The second one is what we live in, and the fragmentation is not finished. It is in progress, and it will keep going until every island is alone. There is a number attached to what we could still theoretically claim, and it is smaller than the 6% suggests. About 6% of the stars in the visible universe are still, in principle, reachable by something leaving here tonight at the speed of light, and that 6% is the most generous possible accounting. It assumes something departs immediately. It assumes it travels at exactly light speed, which nothing with mass can do. It assumes it never slows, never stops, never needs to decelerate at the other end, and that arriving as a beam of radiation counts as arriving. Relax any one of those, and the number falls. Require the traveler to actually stop when it gets there, which any real arrival would, and you lose a large share immediately, because the deceleration eats time, and the line keeps closing during it. Require it to travel at some realistic fraction of light speed, rather than at light speed, and most of the remainder goes. At 10% of light speed, the reachable region shrinks enormously, because the gap has 10 times longer to grow while you cross it. At the speeds anything has actually achieved, the reachable set collapses to our own local group and not much else. So the honest version of the 6% is that it is a theoretical maximum for a massless traveler departing right now, and every realistic constraint you add takes a bite out of it. There is a genuinely strange result buried in this, and it is worth pulling out, because it is the kind of thing that sounds like a paradox and is not. If something did leave here at close to light speed aimed at a distant galaxy, and if it arrived, it would arrive at a place that could no longer send anything back. The trip is one way, permanently, and not because of fuel. By the time you cross that distance, the gap between your destination and your origin would have grown past the point where a signal could return. You would arrive somewhere real, and the place you left would be as unreachable to you as it now is to that galaxy. Leaving is possible, reporting back is not. Anything that ever made that journey would be gone in the completest sense the word allows. Not out of contact, out of causal reach, which is a stronger condition, and permanent. There is a way to see how strange that is by scaling it down to something ordinary. Every place on this world can be reached from every other place. Slowly in some cases, expensively in others, but the connection exists. Anything here can in principle send a message to anything else here and get one back. That is what people mean, without thinking about it, when they say two things are in the same universe. For 94% of what is visible, that is not true and cannot be made true. There is no route, no relay, no patience that closes it. 2 points can both exist, both be real, both be full of things, and have no possible influence on each other in either direction, forever. Physics has a term for that. Those regions are outside each other's light cone, permanently. Nothing that happens in one can ever affect the other in any way, at any time, by any mechanism. They are as separate as two things can be while both existing. And that separation is not a strange edge case at the fringes of the universe. It is the ordinary condition. It applies to the overwhelming majority of everything there is. The connected part, the region where cause and effect still work between here and there, is the small exception. There is one more piece of arithmetic here, and it is the one that lands hardest. Every year of waiting costs targets. A thing that departs 100 years from now can reach less than a thing departing tonight, because the line will have moved in during those 100 years. A thing departing 1,000,000 years from now can reach a great deal less. So delay is not neutral, it is expensive, in a currency nobody can get back. Now the honest waiting, because it is easy to let that sit and sound more meaningful than it is. Nothing built here is going anywhere. That is not pessimism, it is where we are. Nothing has left this solar system except a handful of probes moving at speeds that would need 70,000 years to reach the closest star. No mass can reach light speed. Nothing anybody has ever proposed for crossing interstellar distances has been built or is close to being built. The window of reachable galaxies is closing on a species that cannot reach the next star. That is the sober version, and it deserves to be said, because the alternative is a video that leaves you with the impression that a decision is being missed. No decision is being missed. Nobody has the option. There is a particular way that gets misused, and it is worth flagging, because you will run into it. The numbers in tonight's video get borrowed occasionally to argue that somebody should be hurrying, that every year of delay costs galaxies, so the priority should be leaving as fast as possible. The arithmetic in that argument is correct, and the conclusion does not follow, because it skips the part where nothing can make the trip. The gap between where we are and a ship that could cross millions of light years is not a matter of urgency or funding. It is a matter of physics that nobody has, and possibly physics that does not exist. Hurrying does not close it. 1,000 years of hurrying does not close it. So when you see the closing horizon used as a reason to do something, the honest response is that the horizon is indifferent to what anybody does, and was always going to be. It is a fact about the universe, not an instruction. What is real is the shape of the situation, rather than any lost opportunity. We are inside a region that is being cut off from a larger one, at a rate that can be measured, by a process nobody can influence. The cutting off will complete whether anybody is here or not, and it would complete identically if this world had never produced anything alive at all. That indifference is the part I keep coming back to. None of it is about us. There is no relationship between what happens here and what the universe does. The line closes at the same rate over a world full of civilizations and over a bare rock, and there is a way of holding that which is not bleak, which I want to offer honestly rather than as consolation. The local group is not going anywhere. That is settled, and it is a couple of trillion stars, and it will be there in 100 billion years when everything else is gone. Anything that ever comes from this world has an enormous and permanent estate, and the fact that a much larger one is drifting away does not shrink the one that remains. Nothing is being taken from anybody who could have used it. What is being taken is the view, and the ability to know what the view once showed, which is the real loss in all of this, and it is a loss of information rather than of territory. That is worth being precise about. The galaxies do not stop existing. They carry on, with their stars and whatever is on their worlds, for as long as they would have anyway. Nothing dies because of expansion. What ends is connection. The universe stops being one thing that can in principle know about itself, and becomes a very large number of separate things that cannot. Every island ends up with a complete and self-consistent picture of a universe that is not the one it is in, unless the thing driving all of it is not as steady as everybody has assumed, and there is now real evidence pointing that way. In March of 2025, a project called DESI released results built from nearly 15 million galaxies, and what they suggest is that the thing pushing the universe apart may be getting weaker. If that holds, a large part of tonight is wrong. I want to give it the space it deserves rather than mentioning it and moving on, because it is live, it is contested, and it is the single largest open question in this subject right now. Start with what DESI is doing. In plain terms, it has been building the largest three-dimensional map of the universe anybody has made, not a photograph of the sky, which is flat, but a map with depth, where every galaxy has a position and a distance, 15 million galaxies, out to 11 billion years back. With a map like that, you can do something you cannot do any other way. You can watch how the expansion behaved at different points in the past, because different distances correspond to different eras. Nearby galaxies show you recent behavior. Distant ones show you the behavior of a much younger universe. The assumption for the last 25 years has been that dark energy is a constant, the same amount in every cubic inch of space, unchanging forever. That is the simplest possibility. It fits everything found so far, and it is what produces the picture I have been describing all night. What the map appears to show is that it is not constant. The signal in the results is that the push was stronger in the past and has been weakening. Not dramatically, and not with certainty, but consistently across several independent lines when they are combined. The machine itself is worth a moment because of how it works and because it is a good example of solving a problem with brute mechanical stubbornness. To get a distance for a galaxy, you have to catch its light and spread it out to see how stretched it is. Doing that for one galaxy at a time would take longer than anybody has, so the instrument at the top of a mountain in Arizona has 5,000 tiny robotic arms, each holding an optical fiber, arranged across the focus of the telescope. Before each exposure, all 5,000 reposition themselves, each one moving to sit exactly where a particular galaxy's light will land. The whole array reconfigures in about a minute. Then it collects light from 5,000 galaxies at once, sends all of it down the fibers to be spread out and read, and then the arms move again for the next patch of sky. It does that all night, every clear night, for years. That is how you get to 15 million galaxies. Not with a better telescope, with 5,000 small robots that rearrange themselves every few minutes and never get bored. Now the part that decides how much weight to give the result. The strength of the result, when DESI is combined with other information, ranges from about 2.8 up to a bow. The strength of the result, when DESI is combined with other information, ranges from about 2.8 up to about 4.2 on the scale physicists use for how surprising a result would be if nothing were there. The bar for calling something discovered in physics is 5. That gap matters, and the reason is unglamorous history. Results at 3 and 4 have appeared many times, and a large fraction of them have evaporated when more information came in. Not because anybody was careless, but because at that level, unlucky combinations of ordinary noise produce convincing-looking patterns more often than intuition suggests. So the honest description is that this is a real signal, appearing in more than one place, taken seriously by the people who found it, and not yet at the level where anybody should rearrange their picture of the universe around it. One of the project's own spokespeople put it as the simplest explanation shifting, and that the standard model of cosmology may need modifying. That is careful language, and it is the right amount of confidence. It is worth being clear about what is actually at stake in this for anything alive, because it is easy to treat it as an argument between two groups of specialists. If the push stays constant, everything ends cold and separated. Every island of stars alone, forever, with the last light going out, and nothing after it. Whatever is alive anywhere at that point dies of the universe running down, and nothing follows. If the push weakens and reverses, everything ends hot and together. The expansion stops, everything falls back, and whatever is alive at that point dies in a very different way, and there is at least an argument that something could begin again afterward. If the push strengthens, everything is pulled apart, and it happens far sooner, and to everybody at once. 3 endings. All of them ends, and the difference between them is the largest difference anybody could care about. It is the difference between a universe where nothing can ever happen again and one where something might. Nobody alive now is affected by any of it, not remotely. The nearest of those endings is billions of years out, and this world stops being habitable in one. But it does determine what kind of place this is, and whether everything that has ever happened anywhere is the only round of it there will ever be. That is what 15 million galaxies and 5,000 small robots are actually working on, and it is why a result at 3.5 sigma is worth taking seriously and not worth building a picture of reality around. Now what changes if the weakening holds? Because that is the interesting part. If dark energy weakens over time, then the acceleration slows down, and the line stops closing. At a minimum, the 94% stops climbing. The things currently on the far side stay there, because that is already permanent, but the ongoing loss would stop or slow considerably. Push it further, and stranger outcomes appear. If the push keeps weakening and eventually reverses, gravity wins again. The expansion slows, stops, and turns around, and everything falls back together over an enormous stretch of time. That is a completely different future from the one in this video. Instead of an emptying sky and permanent isolation, everything comes back and ends in something dense and hot, rather than something cold and disconnected. Both of those are on the table right now, and they are opposites, and the difference between them is a measurement that has not yet been made cleanly. there is a third possibility going the other way, and it deserves a mention. If dark energy strengthens instead, the acceleration keeps growing until it overwhelms gravity at smaller and smaller scales. Galaxy groups come apart, then galaxies, then solar systems, then worlds, then atoms. Everything ends by being pulled to pieces in a finite time. That one is currently not favored by the results, and it is the reason people watch this question closely, because the range of possible futures it spans is the widest range in physics. So the honest position tonight is this: the 94% that has already gone is gone. Nothing in the new results changes that, because those crossings already happened under conditions that already applied. What is uncertain is whether the process continues at the rate it has been going, slows, stops or reverses, which means the specific number I opened with is solid and the trajectory it sits on is not. I would rather hand you that than pick whichever version makes the better ending. More information is coming. DESI is still running, and its full survey will roughly double what the current results are built on, and other efforts are approaching the same question from different directions. Several years, not several decades. Which means, and this is the part I would want to know if I were you, that this is a question you'll probably see answered. Not the far future, not the last star, but whether the push is constant or weakening, and therefore which of those endings the universe is heading for, is a question with a realistic chance of being settled inside your lifetime. That is unusual. Most of the genuinely large questions in this subject are not like that. Whether anybody else is out there, what dark matter is, what happened before the beginning, none of those have a date attached. This one does, roughly, and you are alive for it. Whether it comes out one way or the other will not change a single thing about your life. It will change what kind of universe you have been living in the whole time, which is a different sort of thing to find out, and arguably a stranger one. There is something I find genuinely appealing about that, and it is not about the answer. For most of history, questions about the shape and fate of the universe were not questions anybody could investigate. They were positions you held. What has happened in the last century, and particularly in the last 30 years, is that they turned into things you can go and check, and the checking is producing answers nobody expected, and occasionally overturning what everybody was sure of. The acceleration itself was one of those. Nobody predicted it. 2 teams found it while looking for the opposite, and spent months trying to disprove it. If the weakening turns out to be real, it will be the second time in 30 years that this particular question has surprised everybody, and the people who are certain right now will have been wrong twice. That is not a failure of the field, it is the field working. There is a fair question to ask at this point, which is why anybody should believe the 94% if the underlying physics is this unsettled. The answer is that they are different kinds of claim, and it is worth separating them clearly. The 94% is arithmetic about crossings that have already happened. Those galaxies pass the line under conditions that already applied, at expansion rates that have been measured, during a period we can see directly in the record. Changing what dark energy does from here forward does not reach back and reconnect them. The projections are different. How much more is lost, how fast, and what the sky looks like in 100 billion years all depend on the push continuing to behave as it has. That is exactly what is in question. So the past is solid and the future is not, which is the normal condition of this subject, and is worth stating rather than smoothing over. There is a version of this that applies more widely, and I think it is the most useful thing in tonight's video. When somebody tells you something about the universe, it is worth asking which of 2 things they are doing: reporting something that has been seen, or projecting forward from a rule that is assumed to keep holding. Both are legitimate, they carry completely different weight. The acceleration was seen. The vacuum energy calculation failing by 120 orders of magnitude was calculated. Dark matter holding galaxies together was seen. What dark matter actually is has never been seen by anybody. Almost every disagreement in this field is between people who agree about what has been seen and disagree about what follows from it. What is not in doubt is where all of this is heading if nothing changes, and the far future is worth walking through in order, because the sequence is stranger than any single stage of it. The last star in the universe will go out somewhere around 100 trillion years from now, and by then, nobody looking at the sky will have seen another galaxy for a very long time. The order things happen in is worth walking through, because each stage is strange on its own, and the sequence is stranger still. Around 1 billion years from now, this world stops being habitable. The sun brightens, the air fails, and whatever is here either leaves or ends. That is the nearest item on the list, and it is the only one that could concern anything alive now, and it does not really concern you either. 1 billion years is roughly 200 times longer than there have been animals with backbones. Your species has existed for about 300,000 years, which is 1/30% of that. So none of the rest of this list is a forecast about you or anybody you will ever meet. It is a description of what the place you live in does after everything you care about is finished, which is a strange kind of information to have, and is not available to any other species that has ever existed here. Around 4 or 5 billion years, the sun swells into a red giant, swallows the inner worlds, and then sheds its outer layers and collapses into a white dwarf, about the size of this planet. Somewhere in that same window, Andromeda either arrives or does not. Neither of those changes the sky in any lasting way. They are local events. The first genuinely irreversible change comes at around 100 billion years, and it is the one this whole video has been about. By then, the last galaxies outside the local group have been carried past the point where their light can still reach here. The merged remnant of the Milky Way and its neighbors sits alone. The sky above it holds its own stars and nothing else. The leftover glow from the beginning has been stretched out of detectability by the same process. That is the moment the universe becomes unreadable from the inside, and it is permanent, and everything after it happens in a place where nobody can tell what kind of universe they are in. It is worth pausing on what that stage actually means for anybody living through it, because it is the only stage on this list where the change would be noticeable within a civilization's lifetime. It would not be. That is the point. The fading takes hundreds of millions of years per galaxy. No generation would see the sky change. Every generation would inherit a slightly emptier sky than the one before, and would have no way to tell, because the difference across 1,000 years is undetectable. The knowledge that the sky used to be fuller would have to be passed down as a record from a time when somebody could still measure it. And records do not survive 100 billion years. Nothing does. Not written records, not stone, not any material anybody has ever handled, and probably not any institution or language or species. So the loss is not that the galaxies leave, it is that the memory of them leaving cannot be carried across the gap. Whoever is there at the end is not a civilization that forgot. It is a civilization that never had the information, arriving in a universe that had already closed the file. Then a very long quiet stretch. Star formation does not stop at 100 billion years. It slows, because galaxies gradually run out of the gas that makes new stars, and the gas that remains gets locked up in things that never give it back. Small stars keep burning for an extraordinarily long time. The sun gets about 10 billion years. A small red star, using its fuel far more slowly, can burn steadily for something like 10 trillion years, which is 1,000 times longer. So there is an era, lasting for many trillions of years, where the merged galaxy is a dim red object. Very few new stars, enormous numbers of small old ones, each burning slowly, and the whole thing getting gradually fainter. Around 100 trillion years, the last one runs out. It is worth knowing that this is not a thing you could witness even in principle, because of what 100 trillion years does to any notion of witnessing. You get roughly 80 years. Everything you will ever do fits inside that. The entire recorded history of your species, from the first writing to now, is about 5,000 years, which is 60 of your lifetimes end to end. 100 trillion years is 20 billion times that whole recorded history. There is no way to make that feel like anything, and the honest thing is not to try. What can be said is that the universe as you know it, with bright stars and blue skies and things growing, occupies a period so short compared with what follows, that it barely registers as a phase. You are here during the part where the lights are on. That is the end of starlight, not a dramatic end. The universe simply arrives at a point where there is no gas left to make a star and no star left burning, and it does not brighten again. What remains after that is worth listing because the universe is not empty at that point. There are the cooling corpses of stars, white dwarfs, which fade over an unimaginable stretch of time toward black dwarfs, which is a hypothetical object because the universe is not old enough for a single one to have formed yet. Neutron stars, which are the collapsed cores of larger stars, cooling in the same way. And there are black holes, which do not fade, and which end up as the dominant remaining structures because everything else has stopped doing anything. There is something about that era that is worth sitting with, because it lasts far longer than everything before it put together. The universe is 13.8 billion years old right now. The era of starlight runs to roughly 100 trillion years. That means we are about 1 part in 7,000 of the way through the period when stars exist. Almost everything anybody thinks of as the history of the universe, the formation of galaxies, the making of the heavy elements, the appearance of worlds and of anything alive on them, is crammed into the first fraction of a percent of the time stars are burning. We are not in the middle of the story, we are in the opening line of it, and the opening line is where all the interesting chemistry happens, and then there is an extraordinarily long stretch afterward where a dim red galaxy sits alone in the dark and nothing much changes for trillions of years. And even that is the brief part, then a stretch so long that the numbers stop being useful. Some physics suggests that ordinary matter itself is unstable over immensely long timescales, and that protons eventually fall apart. Nobody has ever seen it happen, and the experiments watching for it have set the minimum lifetime at a figure with 34 zeros in it. If it happens, then over a period with something like 40 zeros in it, every remaining solid object dissolves. The dead stars, the worlds, everything made of atoms, simply stops holding together. If it does not happen, they last far longer, and the ending arrives by a different route. Either way, the black holes remain, and then they go too. Black holes are not permanent. They radiate extraordinarily slowly and lose mass doing it. A black hole the mass of the Sun takes something with 67 zeros in it to evaporate completely. The enormous ones at the centers of galaxies take considerably longer. At the far end of that process there is nothing left with structure. No stars, no worlds, no dead stars, no black holes. A universe of scattered particles and radiation, spread across a volume that has been expanding the entire time, at a temperature approaching but never reaching zero. Nothing happens after that, not because time stops, but because there are no differences left anywhere to drive any change. That is where this is heading if the current picture holds, and I want to be careful to label it correctly. The near stages are well supported. The far ones depend on physics that has not been confirmed, and on dark energy continuing to behave as it has, which as of last year is a live question. Now the thing I actually wanted to arrive at, which is smaller than any of that. There will be a last thing anybody sees. If there is anything alive at the far end of this, in that merged galaxy, in the dark, looking outward with whatever it uses to look, then at some point the final galaxy outside its own will fade below what it can pick up. There is no announcement. It fades, over millions of years, and there is no moment where it goes out. But there is a last time it is detected, a final observation of another galaxy, by somebody, and after that, nobody in that region ever sees one again. Nobody will know that observation was the last one. It would look identical to every other faint reading. It would only be identifiable afterward, from the record, by somebody working out that nothing came after it. And then everything that follows for the rest of the history of that place happens in a universe that appears to consist of one island of stars in an endless void, which is precisely what a universe would look like if that were the truth. There is a smaller version of the same thing that is much closer to hand, and I want to leave it with you because it is the only part of tonight you can actually go outside and check. Everything you can see with your eyes belongs to this galaxy, with one exception on a good night, and that exception is Andromeda. It is the furthest thing any person has ever seen without help, 2.5 million light years. A faint grey smudge that will not sharpen no matter how long you look at it. That smudge is the only other galaxy you will ever see with your own eyes, and it is the one that is coming toward us rather than leaving. Every other galaxy that exists, all of the trillions of them, requires equipment, and 94% of those are already beyond reach, and the number climbs by 5,000 stars every second, including while you are outside looking at the one that is not going anywhere. We are, right now, an enormous distance from the end of it, about 100 billion years, which is 7 times the current age of everything. But the direction is fixed. The sky tonight has more in it than any sky that comes after, and that has been true of every night for the last 5 billion years. Let's pull every thread we've followed tonight together, because they arrived in an order chosen for what matters rather than for how the argument is usually built. We started with a number. 94% of the galaxies visible from here are already permanently out of reach, not far away, unreachable by anything, at any speed, forever. And around 160 billion stars cross that line every year, which is roughly 5,000 a second, which means the total fell by more than 1 million while you were listening to the opening. We found that this is not a problem of distance or engineering. Space itself is expanding, so the gap to a distant galaxy grows without anything moving, and past a certain distance it grows faster than light can cross it. A beam of light aimed at one of those galaxies travels forever and never arrives, not because it is slow, but because the road ahead of it is being lengthened faster than it can cover ground. Nothing fixes that. There is no better ship. We found the strangest consequence, and it is not about us. In roughly 100 billion years, everything outside our own gravitationally bound neighborhood will have faded from view, and the leftover glow from the beginning will have been stretched past detectability. Somebody alive then, looking outward with better equipment than ours, and doing everything correctly, would conclude that the universe is a single island of stars in an infinite void, that it is not expanding, and that it has always been this way. Every one of those conclusions would be wrong, and there would be no experiment available to correct them. We found that this puts us somewhere unusual. The universe is 13.8 billion years old, and it stays readable for about 100 billion. We are inside the first 0.1% of the window in which it is possible to work out what kind of universe this is, and we did not arrange that. We simply turned up early. We found that the light still arriving is arriving from things already lost. GNZ11 sent its light 13.4 billion years ago, and is now about 32 billion light years away, and it got through only because it left before the door closed. The route it took shut behind it. The sky is full of things you can see, and nothing can visit. We found that nothing blinks out. Galaxies crossing the line do not vanish. They redden and dim and stretch over an enormous span of time, fading toward a limit rather than disappearing, which means the crossing has always already happened by the time anybody could notice. We found Andromeda coming toward us at 250,000 miles per hour, and the collision that was near certain for 2 decades becoming, last year, close to a coin flip. The mass of our own galaxy is known to about 20%, and a smaller neighbor is pulling us sideways out of the plane, and those uncertainties compound over billions of years. More precise measurements arrive this summer, and it does not change the picture either way, because both galaxies are bound to us regardless, and everything outside that boundary leaves regardless. We found what stays. Around 80 galaxies inside a region 10 million light-years across, held together by gravity that expansion cannot beat, eventually merging into one enormous elliptical that will still be there in 1 trillion years. A couple of trillion stars, roughly 1 part in 500 million of what is currently visible, not poor, closed. We found the discovery itself in 1998 by 2 competing teams who were measuring how fast the expansion was slowing, and both got an answer nobody had on the list. They spent months trying to make it go away. The tool they used rested on a calculation done by a 19-year-old on a boat in 1930, which his own field ridiculed for a decade. We found the 2 lines. We can see out to about 46 billion light-years and reach out to about 16, and everything in between is on the screen and not in the world. And we found the thing that might undo all of it. DESI, 15 million galaxies, a three-dimensional map running 11 billion years back, hinting that dark energy may be weakening rather than constant. Between 2.8 and 4.2 on a scale where 5 is the bar for calling something discovered, real, taken seriously, and not yet enough. If it holds, the line stops closing and a completely different future opens up. And we found, running underneath all of it, how much of this is very recent. In 1920, nobody could settle whether other galaxies existed. In 1924, Edwin Hubble found a variable star inside Andromeda, and the universe went from one galaxy to billions. In 1998, two competing teams found it accelerating, and neither believed it. In 2025, a paper turned the most famous event in this galaxy's future into a coin flip. Every one of those happened inside 100 years. The picture is not settled, and it has never been settled for long. Here is the honest bottom line. The 94% is gone, and nothing changes that. Those crossings already happened, under conditions that already applied, and the new results do not reach back and undo them. What is uncertain is the trajectory. Whether the loss continues at the current rate, slows, stops, or reverses is a question with a live measurement attached and an answer coming within years rather than decades. So the number is solid and the direction is not, and I would rather hand you that than pick whichever version makes the tidier ending. What is also true, and worth holding against the rest of it, is that nothing is being taken from anybody who could have used it. Nothing built here has left this solar system in any serious sense. The galaxies drifting out of reach were never reachable in practice by anything that exists or is close to existing. The loss is not territory, it is information, and the ability to know what the sky once showed. If you carry one thing out of tonight, make it the difference between the two kinds of claim in it. Some of what I have told you was seen. Galaxies exist outside our own, seen. Their light is stretched by an amount that grows with distance, seen. The expansion is accelerating, seen by two teams who did not want it to be. Stars at the edges of galaxies orbit too fast for the visible matter to hold them, seen. The rest was worked out from those, and it depends on rules holding that nobody has confirmed will hold. The 100 billion years, the last star, the final fade, both belong in a video like this. They do not carry the same weight, and almost nobody separates them for you. So come back to where this started. Most of the universe is already gone. That is not a forecast, and it is not a metaphor. It is a description of a line that closed a long time ago on 94% of everything visible, and the line is still moving. You are alive during the small window, when the evidence is still here, when the galaxies are still visible, when their light still shows the stretching, when the glow from the beginning still arrives from every direction. None of that lasts. All of it is on a timer, and the timer has been running for 5 billion years, and it does not reset. The sky above you tonight has more in it than any sky that will ever follow. Thank you for staying with me tonight, or for leaving it on while you slept. Either one is fine. If you want another, subscribe and it'll be here. Somewhere out there, right now, the last light from some particular galaxy is crossing the last of the distance it will ever be able to cross. Nobody will notice. It has been happening about 5,000 times a second for longer than this world has existed. Good night.